Okay, I know that balancing bots aren't exactly new. They've been solved thanks to PID loops for a long time now. But here's the thing. This bot learned how to balance on its own thanks to AI. Welcome to the Reinforcement Learning for Robotics series. I'm going to walk you through the steps and techniques needed to use reinforcement learning, or RL, to train your own robot. My name is Sean Hemel, and I'll be your guide through this journey. I'll show you how to import a model into the MuJoCo simulator, use reinforcement learning to teach that bot to balance, deploy the trained agent to an ESP32-based robot, and even how to combine reinforcement learning with inputs so you end up with a remote control balance bot. There's quite a lot to cover in this series, so let's jump in. Here's what we're going to cover throughout the series. We'll start by seeing how to import 3D models into our simulator program. We'll then use a custom version of CleanRL to train the robot to balance. Note that this will involve multiple phases in something called curriculum learning. From there, we'll see how to take the agent model and deploy it to our hardware. Note that this is where things get tricky, as things in the real world work a little differently than in simulation. This difference is often referred to as the sim-to-real gap, and it's something we'll address in the next episode where we talk about domain randomization. Once we have a mostly balanced bot, we teach it some new tricks by adding commands. This will require retraining using the multiple phases and slowly introducing the bot to different commands. We'll then end by deploying our full command-enabled agent to the robot and building a simple remote control program. As I mentioned, balancing a two-wheeled robot is pretty trivial these days using PID loops. However, learning to use reinforcement learning to teach a bot to balance opens up a new world of possibilities. State-of-the-art research in robotics uses RL to help robots navigate tricky situations in unknown environments. While Boston Dynamics used traditional methods like Model Predictive Control, or MPC, for their dog-like Spot robot, they've started integrating reinforcement learning into their training to help Spot learn to handle new environments on its own. A couple of years ago, Disney released their BDX droids, which involved a lot of research and simulation using, you guessed it, reinforcement learning. The adorable robots learn to walk and express emotions with the help of machine learning. This series will help you get up to speed in the modern techniques used to train RL agents in simulation and deploy them to real hardware. Rather than relying on traditional control methods like PID loops or MPC, reinforcement learning helps train robust agents that can operate in new, unseen environments. By the end, you'll have all the basic tools needed to take this to the next level, which includes training things like quadrupedal or bipedal walking robots. Keep in mind that reinforcement learning is a pretty advanced topic, so I recommend working through the following prerequisites if you're unsure of the math or tools we'll be working with. You should have a decent grasp of probability and statistics. Khan Academy has a good course if you need a refresher. We'll be using neural networks in this series, so you should know a little bit about how to build, train, and use them. The first 3 courses in this Coursera specialization should provide a good foundation for working with such models. We'll be working with PyTorch in Python. I recommend this book by Stevens, Antiga, and Veeman, as it has some really good examples to work through. RL goes beyond supervised and unsupervised machine learning. To get your head around the math, I recommend checking out my blog post series, taking the University of Alberta's Fundamentals of Reinforcement Learning online course, which relies on the seminal textbook by Sutton and Bartow. I also recommend working through my Intro to Reinforcement Learning video, where I review the basics of RL and build a hands-on demo using Gymnasium and Stable Baselines 3. We'll ultimately deploy our code to an ESP32-based robot using Arduino. Becky Stern has a great set of articles and videos on DigiKey's site to get you started there. You'll likely need to create a 3D model of your robot. While any CAD program will do, I'm going to use FreeCAD because that's what I know. While not required, you can check out my Intro to FreeCAD series if you'd like to try it out. You'll also need some hardware if you're following along. In this series, we'll use the M5 Stack Bala 2 Fire Robot Kit. I'll make sure there's a link to it in the description. We're not going to modify it, just attach the wheels and connect the USB cable. There are a number of robot simulation platforms out there for you to choose from. Let's talk about a few of the most popular ones. Gazebo has been around for over 20 years. It has native support for the Robot Operating System, or ROS, but it lacks support for massive parallel reinforcement learning training. PyBullet is the Python interface for Bullet, which is another popular simulator. It's lightweight and easy to use, but development for it has slowed in the last few years. It's also not used much for reinforcement learning and struggles with GPU parallelization. The multi-joint dynamics with contact, or MuJoCo, is extremely popular among RL researchers, and it's the simulator we'll use in this series. It's easy to use, offers great documentation, and plugs in nicely to Python. The downside is that getting GPU parallelization working can be a bit tricky. A few years ago, the Unity game engine was extremely popular for training robots due to its high fidelity, realistic renderings, and ability to use GPU acceleration. However, it's not open source, and another competitor started gaining popularity. NVIDIA's Isaac Sim is probably the most popular platform in industry for simulating environments and training robots. It's incredibly powerful and can easily use GPUs to parallelize training tasks. However, it's closed source, complex to set up, and requires an NVIDIA GPU to use. I definitely recommend keeping an eye on Genesis. It's new to the scene and offers the ability to generate scenes using AI. There are obviously more simulators than the ones I just mentioned, but those seem to be the big players right now. If I missed one that you think is important, please let me know in the comments. In the rest of the episode, I'll walk you through the process of getting a 3D model into the MuJoCo simulator. We'll dive into RL training in the next episode. To start, we need to get some information about the robot. We'll model a simple version of this, so we need to get the width, depth, and height of the chassis. We also need to get the diameter and width of the wheels. I'll do my best to measure where the axles are in relation to the chassis. We also need to know the mass of the 3 parts, so I'll weigh the chassis and wheels on a kitchen scale. I'll record the masses of each in grams. We need to know where the center of mass is for all the parts, as MuJoCo uses this information to simulate the physics for those parts. This information is also crucial for tuning a balance bot. If a part is of uniform density, then we can assume the center of mass is in the same place as the geometric center, or centroid. We can assume our wheels are uniform enough to estimate that the center of mass is right in the middle. The chassis, however, is made up of a combination of plastic, metal, and electronics. The motors and batteries are the densest pieces, and they're located at the bottom. As a result, the center of mass is likely lower than the centroid for the chassis. We can roughly measure the center of mass for a given axis by getting the chassis to balance on a thin edge. It balances pretty well in the center of the X and Y axes, so we can assume the center of mass is in the middle of that plane. For the Z axis, see if you can balance the bot along the X axis on the front or back face. Then measure the distance from the axles. We'll assume that the center point between the axles is the origin for our 3D model. Something to note about the axes: many CAD programs consider the front and back to be along the y-axis. However, MuJoCo and other simulators consider the front and back to be along the x-axis. I'm going to model the bot in FreeCAD with the front and back along the y-axis, but when we import it into MuJoCo, we'll have to translate that to the x-axis. Importing a 3D model into most simulators involves a few steps. First, you'll want to export the various rigid bodies, usually as meshes in STL format. Then, you'll need to get mass and inertia information about those bodies so that the simulator program knows how to simulate their physics. Next, you'll create an XML descriptor file that brings this information together. For MuJoCo, this will be in the MJCF format. For other simulators, it will be the more widely used URDF format. This XML file defines the different bodies by referencing the meshes and assigning physical properties like weight, center of mass, and moment of inertia to each one. It also defines how the bodies are connected to each other, such as through axles or sliders. You can also assign friction parameters to these joints. When that file is fully created, you can then import it into your simulator, which reads it and builds the model using the referenced meshes and joints. At this point, you're ready to start building your AI training program or other control techniques. All of the files for this project can be found in this repository at github.com/seanhemel/reinforcement learning for robotics. If you download the repository and open it up, I'm using VS Code, you want to go into Workspace and you will see Mechanical and Software. Note that there is a lot of code in this series and I won't be going over it line by line, but I recommend digging into it, reading the comments, and going through it if you want to learn more about what I've done. I'm going to give you a broad overview here so you know which files to look at and how to use them, but you are welcome to dig into the files on your own. If you go into Mechanical, FreeCAD is what I'll be working with, so if you use another CAD program, you might want to put another folder here. I'm going to go into Scripts, and I'm going to go into meshexport.py. I'll be honest with you, I had Claude help with a lot of this, but I went through and commented where I could, and hopefully it makes sense as to what's going on. A lot of that was because I didn't really understand the FreeCAD Python API, and AI was very helpful in generating some code that automatically worked with it, and then I just had to make a few tweaks to output what we needed for the meshes. We're going to call this directly in FreeCAD, and we're going to call this export body. We're going to give it the label of the body we want to export. We'll tell it where to store the STL files. Note that we are including an RPY degrees. This allows you to rotate the body, and this is the whole reason we need a specific Python function here rather than just exporting directly from FreeCAD. If you remember, Y-axis is considered front to back in FreeCAD, X-axis is considered front to back in the simulation program in MuJoCo. So we're going to rotate the body by passing in the roll, pitch, and yaw of how we want to rotate that body. We can also strip the placement so that the body ends up on its own origin. So for example, in our FreeCAD document, the wheels are off from the origin, but this will put wheels on their own origin. We're going to leave these linear and angular deviations to their defaults. This controls the tessellation, or how those meshes are discretized into individual triangles. I'm just going to leave it at these sensible defaults for now. Feel free to look through this function to see how that's accomplished. We do it by calling this mesh part mesh from shape, which is part of the FreeCAD library. So we import mesh and mesh part here, and then we essentially just write those STL files out to our computer. And export bodies allows us to do more than one body. Get mesh bounds is mostly used for debugging and checking. And here's where we apply the RPY rotation. Okay, for inertia utils, this is doing something similar where we are calling some FreeCAD API functions, specifically the app, in order to get information about the bodies in FreeCAD. And we are going to export moments of inertia for those bodies. You can get this information in FreeCAD, but it assumes uniform density. So for something like our wheels, that's probably fine. But for things like our chassis where it's not uniform density, we need to call this because the moment of inertia changes due to the fact that the center of mass is different from the centroid. Additionally, we also use this RPY degrees so that we can rotate the part and therefore get the moments of inertia around the different bodies based on the fact that they are rotated for MuJoCo. So we needed a little bit of custom code here in order to make that happen. I will show you how to use these functions in FreeCAD, but feel free to look through this code if you want to see what's going on. In FreeCAD, let's go ahead and go to Open File. We are going to go into our repository workspace mechanical FreeCAD, and then the Bala to Fire is the robot we've been working with. It's the kit. We want to open up the FCSTD file. That should open it up in FreeCAD. As I mentioned, I did a simple CAD mock-up of the little balance bot. You are welcome to use a different CAD program, but I can't promise any of these scripts are going to work for you. As you can see, we have 3 separate bodies. So I'm going to make these disappear. We have our chassis, which is a very simple mock-up of the chassis of our robot. It is not modeling all the things inside. It just kind of assumes it's one body. We also have the left wheel and right wheel. They are essentially the same, but I modeled them as 2 different bodies. You could probably get away with just modeling one and then duplicating that in the simulator, but I like the way this looks in the CAD program. You could spend time making this more exact and modeling it as the robot actually is, but you will find that it will increase your computational complexity during simulation and may not be worth the amount of time spent running the simulation. Also note that MuJoCo uses convex shapes to simulate contact physics. So if we go to the wheel, on the wheel of the actual robot, there's little ridges. When I tried to model that and then import it into MuJoCo, bad things happened. It really just kind of broke the simulator. And that's because it has to use convex shapes to model contact with the ground. You could make little bumps here and make those individual bodies and then import the individual bodies. But once again, that's going to very much increase your computational complexity. So to keep this simple, we're going to assume a smooth wheel, and we're just going to play with the amount of friction that this wheel has on the ground to simulate something like the ridges. So this is one of those sim-to-real gaps you're going to run into with MuJoCo, especially if you're using a very simple model like this for your robot. If you don't have the Python console already up, go to View, go to Panels, and select Python console. So you should have this console right here. I'm going to move this up so you can see this. And for the sake of time, I'm going to just paste these commands in. We're going to say from pathlib import path. This is going to allow us to import the actual scripts that we just looked at. Next, we're going to assign the location of the script's path to this script's path variable. So we're going to say path, and we're going to give it this path. In this case, it's going to be in GitHub, the repository that we downloaded, workspace, mechanical, FreeCAD, and scripts. That's the folder we just looked at. Then we're going to say import sys, and then we're going to say sys.path.insert 0 string and scripts path. This is just essentially adding our path to the Python path so we can import our modules. Next, we're going to import our mesh export. That's the first script that we looked at. Then we are going to tell it the location of where to store the meshes. So in the FreeCAD folder within our workspace here, we're going to go into the Bala2 Fire, which is where we're keeping this FreeCAD file, and we're going to create a new folder called meshes, and it's going to store those meshes in there. Press enter to run that. Then we're going to say RPY. So this is roll, pitch, yaw. And this is just going to be a tuple that is 0 roll, 0 pitch, 90 degrees yaw. That's just going to rotate the body or any body we want to export by 90 degrees so that the y-axis, which is our front and back, becomes the x-axis. So it's just going to rotate it essentially like this when we save those meshes so that front and back lines up along the x-axis in MuJoCo. Press enter to run that. Now we're going to call our actual module function. So we have mesh export, which is from the module we just imported, the export bodies. So there's multiple bodies here. We're going to give it the labels. So we have chassis, which should line up with the chassis label up here. Wheel left, wheel right. These are the bodies here, these rigid bodies that we modeled. We have the output directory, which is meshes path that we created here. And we have the tuple that describes how we want to rotate all of those bodies. So each body gets rotated by 90 degrees individually. Press enter to run that. You should see that it exported those files. So we should have chassis.stl, we should have wheel left.stl, and wheel right.stl. And then we just have some debugging output after that. Next, we need to get the moment of inertia for each of the rigid bodies that we just exported. So we went to import the inertia utils. That is one of the modules that we included in our path here. It's one of the scripts we looked at and custom made. We're going to create a new object called chassis. This is going to be of class body inertia. We're going to tell it which body we want to use, the chassis, which should line up with the model up here. We are going to tell it the mass we measured. Note that this is in kilograms, so this is 127 grams. We're going to give it the measured center of mass. This is XYZ. This is based on where the origin is. So the origin for this should be in the middle between the two motors. So let me turn off wheel left, wheel right. And I'm going to look at chassis. Can I turn on the origin? Yep, there it is. So that's where the origin is. So the origin is right in the center. So if we look at the top, I'm going to move this down so you can kind of see this. So this is in the center, X and Y. And if we put this on its side, you can see that it's where the axles are for the balance bot. So our center of mass is offset from this origin. So it is 0, 0, so it's X, Y, it's in the center. We measured that and verified that, and it should be for a balance bot. And then it is 17 millimeters up from this origin in the Z-axis, so it's right around here. That is where the chassis balanced along that knife edge, and then we measured the distance from the center of the axles up to where that balance point was, and that gives us the center of mass. Again, I did this without the wheels, so it's just the center of mass for the chassis. All right, I'm assuming that ran because it looks like some other stuff is running in the background here. Just to make sure, I'm going to copy and paste this again. I am not an expert in FreeCAD Python console, so if I mess something up, please let me know in the comments. So there we go. We should have this chassis saved as this body inertial object, and we've given it the measured center of mass and how we want to rotate it. So remember, RPY was that roll, pitch, yaw tuple we set earlier, and that's just going to rotate it 90 degrees about the Z-axis, so that the Y-axis in FreeCAD becomes the X-axis in MuJoCo. Now all we need to do is call chassis.summary, and this is all the information we need. This gives you the mass that we measured. That should just be what we entered. The local and global centers of mass, where the body is placed, and then we have the moment of inertia about the center of mass. This is the real information that we need for MuJoCo. And you can see it's just an array, and the only values are along the diagonal here. We can also print this so that we can copy it directly into our XML. If you are creating a URDF file, which is supported by lots of different simulators, but not MuJoCo, then you can call this chassis.toURDF inertial, and this gives you the XML element that you can just copy directly into your URDF file. Similarly, I've got one for MuJoCo, the to MJCF inertial, and you just need to copy this, and that's going to be pasted directly into our MJCF file. Now we need to do the same thing for one of the wheels. I'm going to take the right wheel, so we're going to create another body inertial object. I'm going to call it wheel. We're going to input the measured mass, so that's 17 grams for the wheel, and then we're also going to give it that RPY, which just says rotate 90 degrees about the Z-axis. So run that, we have that wheel object. We're going to say wheel.summary. This gives us that information. And if we want to generate the URDF, moment of inertia information, we have that here. And if you want to do it for MJCF, we can run that function. And this is what we want to copy for our wheel information. Notice here it's giving us the moment of inertia, and it's just the diagonal. That's all it cares about. So it's ignoring any of the elements in the matrix that are not along the diagonal. So these values should line up with the diagonal. MuJoCo uses that information to figure out how the wheels or the chassis move when given pushes or knocked about or bumps. Those moments of inertia are absolutely necessary for the physics simulation. With that information, we can start constructing the XML files that bring in the 3D model along with the physics information into the simulator. Something to note about the bala to fire is that the IMU is not in the direct center of the chassis. That will affect the measurements as the robot tips back and forth. We need to know where it's located. So I've opened up the robot, and on the top PCB under the LCD, you'll see the IMU. I took measurements from the sides to figure out how far away it is from the center in the X and Y plane. I also measured how high it is above the center of the axles along the Z-axis. We'll need this information for the next part. Back in VS Code, let's close down our FreeCAD Python scripts. We are going to go into the Bella2Fire directory in Mechanical and FreeCAD. If you go to Meshes, you can see the .stl files that we saved. You can ignore the step files. I believe I was playing with those to see if those would import a little better, but STL works just fine. These were outputted by our save mesh or export meshes script that we called in FreeCAD. So we can just ignore that for now, but you need to know those locations. If you were working in another simulator, something that's not MuJoCo, that supports URDF, I have an example URDF file here. This is just XML that describes what they call a tree of rigid bodies. So for example, we've got the chassis. We are going to tell it where to find that mesh, in this case, the .stl file. So it is relative to this location, so it just goes into meshes, finds this here. We give it the scale, so we convert to meters basically. We can give it a color. We can provide a collision body. We can define the mass properties. This defines the origin of the body and that moment of inertia. This is the information we got from FreeCAD when we ran those scripts. So within that robot body, so if you scroll up, we've got the robot body and the name here. We have another component. This is wheel left, and we call this a link. So we give it the visual. Once again, this is where to pull that STL file from. We can give it a color, and we can say how it collides with things. We also give it that moment of inertia. We do the same thing with the right wheel. It's mostly just a copy. Feel free to use a different wheel if you want, which we've done here with wheel right. Again, we have the color, the location of the mesh, and that moment of inertia. We then specify the joints, how things are connected. You're welcome to look through here, but this is where we specify how the wheels are connected to the chassis. So we have the left wheel joint here and the right wheel joint here. These are essentially the same with just different connecting points. I just commented one a little better than the other. You will find that URDF files are a little simpler because then you specify other parameters inside of the simulator. Let's go on to the MJCF file. Note the extension difference. So this is just XML. They both are XML, but a lot of times the simulators want .urdf to know what it's looking at. XML is the extension you'll find for MuJoCo. I've commented this through, so feel free to look through this. You'll find that these MJCF files have a little bit more information in them than URDF because this is where you specify a lot of the parameters to describe how the robot works. Since we're working with MuJoCo, let's go through this. We have to set some global parameters for MuJoCo. For example, we want to use radians instead of degrees. We specify the coordinate system, whether we express things locally, I guess to each of the bodies, versus globally or in the absolute frame. We also specify where it can find those STL files, so it can find them in the meshes that is relative to this MJCF file. And then we usually want to set auto limits to true, which automatically limits the movement of the connected bodies when we specify joints and give a range of motions for that joint. We also set the options here. This is incredibly important. This says that each time step in MuJoCo is 5 milliseconds, so it recomputes the physics every 5 milliseconds. This must exactly line up with how we do things in reinforcement learning. So when we go to our PPO algorithm, we must understand that the time steps computed there are also 5 milliseconds. And when we deploy to our firmware, we must ensure that our time steps there are also 5 milliseconds, which means that we take a reading, we perform inference to figure out which action we want to take, and we need to take that action all within 5 milliseconds. If you're finding that you cannot accomplish that in firmware, for example, your microcontroller is too slow or inference takes too long because the neural networks are too big, then you will have to come back to this option right here and increase the time step and hope it doesn't ruin the robotics as you retrain everything. So this is an incredibly important parameter. We also set what gravity is. That's a useful thing to know. And I believe that implicit fast is just the default algorithm used for position and velocity. So we'll just leave that. You can also set up some defaults. So if you don't want to rewrite a bunch of code down here, you have this option of using this default tag. Note that we're under this MuJoCo header here, where we're defining everything under that before we start defining the world body. So this is just setting things up in this MuJoCo simulator options. You will see that geometry is referred to as a geome in MuJoCo. This refers to a lot of bodies. So you can see like the chassis geome here, and it acts as kind of a container for both the mesh and the physics and how it's rendered and how it computes contact and so on. So that's what a geome is. Contact is calculated using these bit masks. So you can assign different geomes to different groups and say that some geometry contacts or collides with other geometry, but not with another group. So you can use those bit masks to assign how things contact with each other. This is a simple robot. We're going to say everything can contact with everything, including the ground. We also just came up with a reasonable estimate of what friction looks like. The main friction that we care about is having the rubber tires hit a floor or desk. So we just said 0.8 here. It's a general estimate. Later in the series, we're going to vary this in something called domain randomization so that the robot learns to deal with different types of floors or different types of friction. Here's where we start defining the robot. So we give the mesh a name, we tell it where to find it. Remember, we've already set the meshes directory up here. So it looks in meshes, finds that chassis.stl. So that's what it's using to render the chassis. We also make sure everything is specified in meters. So we scale everything. If I remember, FreeCAD wants to specify things in millimeters, so we need to scale all of that to meters. We do the same for the left wheel and the right wheel as well. Here we're setting up the world around us. So a skybox is just how we're going to draw the sky. This isn't really important, but it makes for nice visualization. We're going to do the same for the ground. It's just a basic grid. We give it some generic colors, and we make it pretty big that the robot can drive around on, hopefully an infinite plane. If it drives too far, well, I think it just drives off the rendering, and it's still considered driving on the ground, even if it looks like it's driving off into space. But this is just for rendering and visualization. And we do the same thing here. We're just defining what this grid looks like. All right, that's it for the assets that we have created here. So you see that we have this assets, I guess, container or header, and we define those here because we can use those as we construct the robot and the world around it. So the world body essentially is everything, and everything kind of works as a tree under this world body. We can define some lighting if you want to. We can define that ground plane. Notice we assign a material here, which comes from our grid asset that we defined up here. So in this world body, we define another body named the chassis. So this is the chassis of the robot. We give it a position, which is going to be at the origin, and we raise it up 22.5 millimeters. Remember, the origin of the chassis is that point in between the axles, and we have to offset it by the radius of the wheels so it sits at the right height. We then create a free joint. This is a specific type of joint that can translate and orient freely within the world frame. So basically we're saying the robot can move anywhere within the world frame. It's just a free joint that can move in any direction, any orientation. We then define some collision here and some visuals. So we have a geome here. We'd say it's a type of mesh, and we tell it which mesh to use, which is something we defined up here, the chassis mesh, which pulled in from this chassis.stl file. So that's how it's being rendered based on that mesh we exported from FreeCAD. We're going to give it a color. This should be a red that kind of matches what the actual robot looks like. I initially made it transparent so we can see the IMU. That's not the case anymore. I'm going to actually get rid of that comment, but feel free to change that 1.0, this alpha, into something else if you want to look inside of it. We can also manipulate how MuJoCo is rendering so we can look at like a wireframe view if we want to peer inside the robot to see where the IMU site is. This is where we paste in that moment of inertia for the chassis that we got from FreeCAD when we ran our Python scripts. So we just paste that in there. Note that this diagonal or diag inertia element should line up with the moment of inertia we saw in FreeCAD. We then want to specify a site for an IMU. This is something that is different from the URDF files, where you would not specify it in the XML. You would specify this IMU site in the simulator itself. But MuJoCo wants the, for example, sensors specified here. We're going to create a place for the IMU. We're just going to say it's a really basic box. We're going to give it a position and a size. I estimated the size based on measuring the actual IMU on the PCB on the robot, and it's about 3 millimeters by 3 millimeters, and it's about 0.35 millimeters high based on what I could get with my calipers. We also have this measured position. The IMU should sit just under the top of the robot or under that LCD, and it should be off to one side. And this is the position that I measured based on the actual robot. When we look in MuJoCo, you should see a little blue box based on the color we gave here. That is the size of the actual IMU sitting at the correct position based on where we measured in the actual robot. This makes a big difference when the robot is learning to balance. The IMU location determines how it's measuring tilt within the robot. So keep that in mind. This should line up with what you physically measure, where the location of the IMU is in the real robot. I'm going to add this real basic green box to the front of the robot so we know where front is, because the robot is symmetrical, so the front and back look the same in simulation. I want to keep track of where the front is of the robot so we can see and make sure it is driving in the correct direction as we predict, especially when we get to the control part. Then we have this left wheel body. You'll notice it is still under this chassis. So this is how we're creating the tree. The world body is the root of the tree. Then we can have bodies within there. And then underneath the chassis, we have the left and right wheels, and we connect them to the node above it. So we give the left wheel a position that tells it where to attach the body to the chassis body. We specify a joint. We're not going to use a free joint like we did for the chassis. Instead, we're going to use a hinge joint. And we essentially set it so that it can only rotate around that particular joint. In other words, the wheel is moving on an axle. We give it some friction and some dampening so that the physics knows how to calculate that or simulate that. We also estimate the armature here. This is the motor's rotational inertia as it's reflected through the gearbox. So the gearbox itself is going to provide a level of inertia, and we are just estimating what that looks like here. This affects how the wheels operate in the simulation because that gearbox has some inertia associated with it. So we are just mostly estimating that here based on what we could figure out through that N20 motor with a particular gearbox attached to it. So we had to look that gearbox up and estimate that here. And if I remember, I think it's a 1:30. So the N20 motor, based on the data sheets, starts with this, then we add that 1:30 gearbox, we square that in order to get this rotational inertia as it's reflected through that gearbox. This becomes important because it is higher than the wheel's inertia, especially as we're trying to spin things up. So that provides an important parameter for the physics simulation so that the robot can learn to drive correctly. We're also going to assign the mesh. We're going to give it a color, which is like a dark gray. Once again, the mesh, we tell it to use this mesh asset, which if you come back up here to our assets, we defined this mesh name here, and it knows where to find that STL file, which is wheel left right there. Let's go back down. With that, we also copy in our moment of inertia that we got from the FreeCAD script, and that closes out the wheel left body. Underneath the chassis again, we start this wheel right. It's the same information, it's just mounted in a different location, which is given by this position parameter here. From there, we close out the chassis body, we close out the world body, and we are done. Then we define our actuators. Even though we've specified the joints when we connected the bodies together, we did not specify that those joints are actively controlled by a motor, a servo, or any other kind of control unit. We just call them actuators for robotics. So we need to specify those active control areas here. So we're going to have two, one for the left motor, one for the right motor, and those are connected to the wheel joints for the left and right wheels. Normally in MuJoCo, you would specify a gearing ratio, and then you would give it a control range, and that would lead to the ultimate torque applied to those axles or those joints. While you can measure this, I estimated that with the gearing on these N20 motors on the robot, we get about 0.05 Newton meters. We're going to say that in full reverse, you get negative 0.05 Newton meters, and full forward, you get 0.05 Newton meters. This is just a back and napkin estimation from our N20 motor with that 1 to 30 gearbox. When we go to domain randomization, we're going to randomize this so that the reinforcement learning algorithm learns to deal with this potentially not being exactly correct. Note that for reinforcement learning, you often want to set your control range to be something that's normalized. So while generally MuJoCo, you would set this to be your desired torque or power to the motors and then let the gearing deal with that difference as it's applied to the axles, in reality, we're going to make it so that the control range is -1 to 1. We're going to normalize that and then use this gearing parameter to fix that so that -1 times this gear equals the estimated torque at the motor in reverse, and then +1 times that gearing gives us 0.05 Newton meters. That's full forward based on what we think the motors can handle. So we're using this to kind of flub what the simulator is doing so that we can actually apply a normalized control range for reinforcement learning. We're going to do the same thing for the right motor. These are just the same, they just apply to different joints. Finally, we're going to define all the sensors and their locations. So we created an IMU site under the chassis. So it's part of this body tree that makes up the robot here. So we have an IMU site, but we didn't specify that it's actually an IMU. So we're going to place two different sensors. Note that an IMU is really a collection of sensors. One is going to be an accelerometer. We're going to call it IMU Accel, and we're going to place it at that IMU site. We're going to do the same with a gyroscope. We're going to call it IMU Gyro and place it at the same site. If you are curious, MuJoCo has built-in sensors. So that's why we are using these tags here, accelerometer and gyro. If you want to know where we're getting any of these tags, you can go to mujoco.readthedocs.io and you can look through the modeling here. This shows you how to specify all of that XML information. So you can go to XML reference and you can see all of this. You can drop these down. So for example, if we go to sensor, you can see here's where we're getting these tags. It has a bunch of built-in different sensor types. So accelerometer is one, and you can see the elements or the parameters that this tag requires that we want to set up. So we need to give it a name, we need to give it a site, and you can specify some other things. If you go to sensors, you can read more about those parameters. So this is where we're getting that information when we are setting up this XML file for MuJoCo. With that in mind, we also specify some wheel encoders where we can get the position and the velocity. And we're getting that information from those joints. If we go back to the XML reference, we can go to sensor. You can see joint position, joint velocity here, and you can read about those different tags in the docs here. With that, we close out of our MuJoCo tag. I'm going to go ahead and save since I made that comment change, and we are ready to move on to actually simulating our robot. While you can install MuJoCo and Python and PyTorch, all of these locally, I'm going to show you how to do it with a pre-configured Docker image so that I could control all of the versions and ensure it's going to work the same for you. So you don't have to do the Docker stuff, but I recommend it because it's guaranteed to work across a variety of operating systems, and I've frozen all of the versions. So if you don't already have Docker, head to docker.com. We're going to download the Docker Desktop app. So go to Products, go to Docker Desktop, and click on the Download Docker Desktop for your particular operating system. Run the installer. With that installed, we can now go to a command line prompt and build the image. If you're on Windows, I recommend going to WSL. You're going to probably have to have that installed for Docker anyway. If you're on Linux or Mac, just bring up a terminal window. Navigate to the repository that we've been working in. If you look in there, you will see dockerfile.bar and dockerfile.cpu. The .bar file was used for some testing, so you can ignore that. The .cpu builds an image for running PyTorch and reinforcement learning using MuJoCo on the CPU. Getting GPU support for MuJoCo is a little tricky. In the future, I might have a .gpu version that you can use that relies on GPU parallelization to make things a little faster if you've got a GPU that you can use. But for now, we're just going to run everything on our CPU. Then we're going to call docker build-t, give it the tag rl robotics, specify the file dockerfile.cpu. We're going to let that build. Mine's already built, so this should be pretty quick for me, but for you, this might take up to an hour because there's a lot of things it needs to install. We're then going to call docker run. We're going to say interactive mode with -it. We're going to say completely remove --rm the container when we're done. So don't save anything locally to that container. It will get deleted. You'll want to save everything to the /workspace directory that you can see we mounted with the -v parameter. We're also going to expose ports 3000 and 6006. 3000 is for the webtop browser interface. 6006 is for TensorBoard, if you want to watch your training in progress. We also mount that local workspace directory so you can save your work. And I'm going to increase the shared memory size to 2 gigs because I find this process of training a RL agent takes up a lot of shared memory. MuJoCo also uses a lot of memory. And we're going to specify the tag of the image we just created, so RL Robotics. Let that run. It should take a moment to boot up. Once the image is running, go ahead and bring up a browser and navigate to localhost :3000. That should bring up a webtop image. I did my best to put icons here to make quick shortcuts for the things you might want to use in here. There is a very weird bug where it is duplicating my icons that I created. I tried to solve this bug with not much luck. So if you figure out how to remove these extra icons when WebTop starts, please let me know in the comments. Otherwise, we will just move forward with using these applications here. We're going to go ahead and open up Jupyter Lab. That should start a terminal and bring up this browser interface inside the container for us. This should mount workspace. Note that anything you save within here is saved to your host machine, so you don't need to worry about losing your work. We're going to go into software. You can see that I've labeled the folders in the software in workspace to line up with the various episodes in this series. So as we work through them, we're going to go through here. There's also some shared RL, and this was an old runs where I was testing some things, so you can ignore that. That should not get checked in. But RL is the main reinforcement learning algorithm we'll use throughout the series. But otherwise, we're going to work in order here. So for this episode, episode 1, we're going to go into this test model in MuJoCo. We're going to go to test motion. And this is the notebook we're going to be looking at and using. If you have not used Jupyter Notebook or Jupyter Labs before, it's just a collection of cells that run Python in chunks. So press Shift-Enter to run a cell. This is just a documentation cell, so nothing runs here. We are going to import some standard libraries along with some third-party stuff, including the ability to display things from Jupyter. And we're going to import MuJoCo. What's interesting is that MuJoCo is not really a separate application that gets run. It is meant to be called from Python. So we're going to import MuJoCo and the viewer so that we can fire up MuJoCo within Python, and then it shows up as a viewer on the side that we can then interact with. So let's go ahead and run that cell. We're going to create some settings. We're going to specify that MJCF file path. This is that XML file we were just looking at. Let me close this sidebar so you can see this full line. So this is how MuJoCo pulls in that MJCF file in order to set up the robot and the environment. In this program, we are going to do a simple button control system. You're going to see how incredibly difficult it is to try to balance the robot manually so that when you push the up and down arrow keys, it tries to increase or decrease the speed of the robot. We need to make sure that the names match up with the names of the bodies that we specified in the MJCF file, so left motor, right motor. We also need the sensor names to line up with the names of the sensors we specified in that MJCF file. So make sure these names are correct from that file. And here we're just assigning the key numbers. So Shift-Enter to run that. We're going to set the robot to initially be left and right. A simple clamping mechanism so the motors can't go over or under a certain speed limit. Here's where we handle the key presses. So we have key up, key down, backspace simply resets MuJoCo along with resetting the robot to be 0 velocity. Here's how we actually load the model into MuJoCo. We say MuJoCo, this module, mjmodel.from XML path, and we're going to give it the path location of the MJCF file. And then that loads in the model. Then we take that model object and we pass it into this MuJoCo.mjdata so we can get this information about the simulation state. So these are the two main functions you need to call in order to import your model and that MJCF parameter file into MuJoCo before we start it up. Next, we're going to get IDs. The IDs are numbers that MuJoCo assigns to things like joints and bodies. So we can use functions from within MuJoCo. We can pass in the name, like left motor. We're going to say this is an actuator. We're going to give it the model that we specified right here, and it's going to give us the IDs of those actuators, which we need for code later on. So it'll print those out. These are the IDs of the left and right motors. Here is where we actually simulate stuff. So we're going to reset the data to start. That just sets everything back to the defaults that we specified and resets the robot back to the origin. Then we're going to launch the simulator and it's going to fire up a GUI for us. We do that by calling this with MuJoCo.viewer.launch passive. We pass in the model, we pass in the data. That's what we specified up here. We specify that key callback function. So when keys are pressed, it calls these. And we're going to call this the viewer. So in here, we define the camera parameters. We can set where that camera is, where it's looking initially. And then we run this, I'm going to call it a forever loop, but we can exit it if we want to. So here's the loop that runs for our simulation. We get our step time. For every step in this loop, we get this global dictionary that we assigned for the control. Left motor, right motor, starts at 0. When that gets changed, those values are just written to the actual control of the robot so that it starts moving the motors. We advance the simulation by 1 step. Remember, this is controlled by that time step attribute in the MJCF file, which should be 5 milliseconds. We then render the current simulation state, so that updates what we see in the viewer. We then print the sensor readings. Every so often, we don't want to print it every step because that will just flood our output. So we have this print every. And if we look up here, every 50 steps, it gets printed. Okay. So with that, we read our sensors and we just print those to the console. If we want to view the simulator in real time, we can have it wait the rest of those 5 milliseconds. So we just sleep the amount of time that's left. Note that if we get rid of this, the simulator will run as fast as possible. That's useful for training when we don't care about watching it in real time. But since we're doing this in real time, we will want to make 5 milliseconds look like 5 milliseconds. So let's press Shift-Enter. We're going to run that. Our simulator comes up. We can use the mouse to zoom in, rotate the camera, rotate it around by pushing the left and right mouse buttons. And you can see that all that happens is the robot just falls down. I'm going to push W in order to see the wireframe view. And I'm going to rotate this around. And you can see the little blue box here, that is the IMU site with our little blue box denoting where the IMU is, and that should line up with the actual location of the IMU in the real robot. There's also this little green box that we put on front that doesn't do anything. It just tells us where the front of the robot is. That's useful for training, especially later when we want to know if the robot is actually driving backward or forward, because otherwise the robot is symmetrical and it's hard to tell. I'm going to push W again. So we go back to this full 3D rendering mode. I'm going to zoom back out, push backspace, that resets the robot, and I'm going to try to use my arrow keys and balance the robot here every time resetting with backspace. Oh my goodness, this is incredibly difficult to try to get the robot to balance. I got it to... this is so hard. Feel free to try this out for yourself. When you're done, you can just come over to the cell that's running here. You can see the information getting printed out from the sensors. In fact, if I reset again, you can see those reset. I'm gonna try to drive the robot, and you can see how those sensor readings change. When I'm done, I'm just gonna push the interrupt or the stop button here. That's going to shut down MuJoCo. That viewer will exit, and we are done. Before I give you a challenge, you should know that shutting down the container requires manually stopping the container from Docker Desktop. This is a known issue with WebTop. You cannot press Control-C from the terminal here. Instead, you have to bring up Docker Desktop, the actual application here. Wherever you are in here, you should go to Containers. You should see the container that's running. You need to press the Stop button. In a moment, you should see it stop. Your terminal will finally exit out of that program, giving you a command prompt, and you should see that container disappear, which means everything was cleaned up. If you would like to try the challenge, try writing a simple PID controller to balance the robot. You don't need to worry about having it stay on the origin, so it can drift some, but it needs to stay upright. I highly recommend watching my What is a PID controller video if you need a refresher on the concept. I also have this other video showing you how to tune a PID controller. Spoiler, a balance bot is pretty much just an inverted pendulum on wheels. I hope this helps you see how you can create a digital twin of your robot and import it into a simulator like MuJoCo. In the next episode, we'll dive into actual reinforcement learning to teach our robot to balance. See you then.